Looking at question number 2, it says let the random variable x represent the number of phone lines in use in a technical support center of a software manufacturer at noon each day. Here's the probability distribution and calculate the expected value or the mean of x. So the expected value or the mean is calculated by taking each of the numbers and multiplying them by their respective probabilities. And it's okay to use these ellipses as you write. If I used my calculator or my super brain, I get that that's 1.6. I'll show you real quick how to do this on the calculator. So I've typed all the numbers into my calculator in L1 and L2. Now, one way to do this would be to simply take all the numbers in L1 and multiply them by L2, and then add up those numbers there. So second list, math, number 5. The sum of L3 is 1.6. A more expedient way is to think that this is really a one variable graph. Even though I've got two lists there, it's one variable. The variable is how many calls or how many phone lines were in use at noon. And so I can press stat calc 1var stats, because it's only one variable, where the list is in L1 and the frequency or how often they occurred is in L2. Calculate, chicka chicka whir, there's the 1.6 right there. Question number 2 says, using past records, we selected 20 random days and found an average of 1.25 lines. What if instead we looked at 1,000 days and found the average there? How would you expect the new average to compare to the first sample? So I would expect the new average, or the average of the new sample, to be closer to the true value of 1.6. This is because when I look at 1,000, the variability is reduced. So the mean is closer to the true mean, or to the parameter. Now, letter C defines a median, and they might define it slightly differently than you're used to. What they say here is it's the median if the values at or below it are greater than or equal to 50%, or the values at or above it are greater than or equal to 50%. So, here's a table there. And I notice if I just pick a number, for example, so I'll start with this one. How much of the data is at or above 1? How much of the data is here? 20, 35, 45, 50, 60, 65? 65%. How much is at or below that number? Well, that's 35 and 20, 55. That actually satisfies it. The median is 1. If you had to justify it, you'd say since 55% of the data is less than that number and 65% of the data is greater than that number. The next part says, in a sentence or two, comment on the relationship between the mean and the median relative to the shape. So I saw in part C that the median was 1. I remember from part A that the mean is 1.6. So since the mean is bigger than the median, the distribution is right skewed. And then we could go back and look at this distribution here. Let me erase a little bit of this. And I can see that the distribution, if I made little bars above it perhaps, this one goes up 0.35, 0.2, 0.15, and 0.15, 0.1, 0.5. Sure enough, right skewed distribution. So this next part wants to know what the probability is that 3 or more lines are in use. And so what that means is, what's the probability we pick a day over here? So that's going to be 0.15 plus 0.10 plus 0.05, or 30%. F says what's the probability at least one line is in use. That's all of this, which is also this. And then G gets interesting. It says given that 3 or more lines are in use. So in other words, given that you're over here, we already found that that was 30% of the time. What's the probability all 5? What's the probability of this? Which reduces to 1/6 or 0.16 repeating. Letter H. Assuming the days are independent, what's the probability exactly 2 of the next 5 have no lines in use? This is a binomial question. And it's binomial. You might recall there are 4 characteristics that our book abbreviated BINS. The first one is binary, or a success and a failure. You either have no lines or it's not no lines. The I is for independence of each observation. The N is a fixed number of observations, in this case 5, and the S is for a set probability. And that probability where there's no lines in use is 35%. You can see right there, no lines in use, 35%. And so we have a binomial situation. And if you were using your calculator, you could just do it like this. The binom, right? The binom PDF of NPX. If you had to show your formula, the probability X is 2 is 5 choose 2, no horizontal line in there. Probability of success, and we succeeded twice. The probability of failure, and we failed the rest of those times. Now you might choose right here to write 0.65 and right here to write 3. That's okay. And either way you work this out, then you get 0.336. Letter I says, suppose you come every day and you want to know what are the chances you don't find all 5 in use until your 7th visit. So I had to think about this for a second. I said, well, what that means is the first day it was not all 5, and the second day it was not all 5, and the third, and the fourth, and the fifth, and the 6th. And then on the 7th day, it was all 5. Maybe I shouldn't use an exclamation point because it's not factorial. It's just me being excited. So what's the probability? Now, if the days are all independent, then I can just multiply these probabilities together. And the probability it was not all 5 is this. So it's 95% and 95% and 95%. And then all 5 is 5%. I could simplify this by saying it was 95% 6 times, and then the 7th time it was that. And when I work out that, I get 0.03675, or 3.675%. Letter J, find the standard deviation of the number in lines in use. Might have to go back and remember this formula, but it looks like this. It's the standard deviation is going to be the square root, and so maybe I'll find the variance first. That might be easier for me to write. It's each number minus the mean squared times its probability of happening, plus the next number minus the mean. Remember, the mean from part A is 1.6. All the way until I get to the last number minus the mean squared times its probability of happening. And then when I do all that, I take the square root of all that, and I find that probability, the square root of that variance is the standard deviation, which is 1.56. Now I could also do this on my calculator. See, here's actually, I still got it, my one variable stats, and there's the 1.56 right here. That's the standard deviation of all of that. Now on letter K, it says each call lasts 3.75 minutes. So if I examine the calls that are going on at noon, what's the mean and the standard deviation for how long those calls lasted? Well, the mean is going to be, there's 1.6 calls that are going on times an average of 3.75 minutes. And so that's going to be 6 minutes. Standard deviation works the same way. Standard deviation was 1.56, and .75 minutes per question is 5.85 minutes. And that's because when I multiply by something, it changes the locations, such as the mean or the median or the minimum or the maximum, by that factor. And likewise, when I multiply by something, it changes those measures of spread, such as the standard deviation or the IQR, by that same factor. Now, let me give you a bonus question that wasn't on here. What if everybody on the phone call agrees to one of those 1-minute surveys at the end of the call for quality control? So everybody's going to do it. So we've added 1 more minute to everybody's call. What's going to happen to this 6 minutes? Well, it's going to go to 7 minutes, right? Now, what's going to happen to the spread? Well, the spread actually isn't going to change because all of the calls shifted by 1 minute. So how spread out those calls, those minutes are, stays the same. L. All right, what if we do this for 7 days? What's the total mean and standard deviation going to be? Okay, so here's how I thought about it. We have, I'll call them Sunday through Saturday. So we have the mean of Sunday plus the mean of Monday plus the mean of Tuesday, all the way down to the mean of Saturday again. Now, if all these days are actually independent, then all of these numbers were 1.6 or 7 of these numbers right here, which gives me an average of 11.2 lines in use. It also wanted me to find the standard deviation. This one's a little trickier. So I've got the standard deviation of Sunday and the standard deviation of Monday and the standard deviation of Tuesday and the standard deviation of Saturday. But I can't add standard deviations. I can, however, add variances if the days are independent of one another. So if the days are independent of one another, then my new variance, so this is going to be the variance, not the standard deviation, is going to be 1.56 squared times 7. There's 7 of those dudes. And if I work that out, 1.56 squared times 7, that's 17.0352. And so the standard deviation is the square root of that, which is 4.13. Now, letter M says, suppose another support center has a mean of 2.1 and a standard deviation of 1.8. What are the mean and standard deviations of the combination of these two? So here I've got a clean sheet now. So I've got the first call center A was 1.6 and 1.56. And call center B is 2.1 and 1.8. And so this question says, well, what about this? Well, that's just that. So it's 1.6 plus 2.1 is 3.7 lines in use. Now, if these call centers are independent, then this is going to be the same as this. So remember, we had to look at the variances, add the variances, and square root it. So it's the square root of 1.56 squared plus 1.8 squared, which works out to be 2.38. These are number of lines in use. And again, let me give you one little bonus question off of this for part M. What if part N said, what about the difference? So what is this going to be? In fact, let me do it this way, because I see call center B has a few more calls. So let's do it like this. How's that going to look? Well, this is just going to be this, as you would expect. So there's the difference. Call center B has an average of half a call more. All right, so how about this guy down here? What's going to happen here? Interestingly, this one is the same as part M. So it's 2.38 lines. And that's because, if you recall, we've said this, the variance of x plus y, if they're independent, is the variance of x plus the variance of y. But we also said this, the variance of x minus y is also the variance of x plus the variance of y. And that's a little bit of a confusing issue. These formulas are true if x and y are independent of each other.